Good morning, everyone, and thanks for coming out. My name's Ben Hamner, and I'm the CTO of Kaggle, and I'm here to talk to you today about a broad overview of our platform and how it may help you in your day-to-day work. But before I get started, I'd like to get a better understanding of who's in the room and what your background is. So I'm going to ask a series of questions about your exposure to Kaggle so far, and I want to raise your hand if you're familiar or have done some of these actions in Kaggle first. So first, can you raise your hand if you've heard of Kaggle? Okay. I might have to stop asking that question because I think that was the entire room. Can you keep your hand up if you have a Kaggle account? Wow. Okay, about 3/4 of the room probably. Then who has downloaded data from Kaggle? Probably about half the room now. And who has entered a Kaggle competition before? Cool, about 30% of the room maybe. Who has won a Kaggle competition or won prize money in a Kaggle competition? One person at least. Awesome, I can have you come up and give the talk instead. And then have you written and run code on Kaggle through Kaggle kernels? Raise your hand if you have. Okay, about 10 people maybe, about 5% of the room. And then have you found Kaggle helpful to learn about data and machine learning? Okay, about probably 40% of the room. And then finally, do you use Kaggle as your primary resource when you're starting your journey into data science and machine learning or starting to work with data? 3 or 4 people. Okay, cool. So small number of people. Thanks for that to get started. And then as a bit of background, Kaggle is the world's largest online community of data scientists, machine learning engineers, and AI engineers. And we have about 2.8 million users who come to Kaggle for 3 main motivations. First, to learn and improve their skills working with data and starting to work on machine learning and AI problems through a mix of learning from content that we create, content that our users publish, as well as competitions that we put up that provide great test beds for sharpening your skills. Secondly, to compete in the machine learning competitions that we host and demonstrate how your methodologies and techniques work in a fair playing ground to evaluate them compared to thousands of other users around the world. And then finally, to collaborate on data and AI projects as an individual or as part of small teams as you work on sharing and collaborating on code to analyze data. And we started hosting AI competitions in 2010, and for most of our history, we've been really focused on hosting these competitions where companies, nonprofits, and research groups would come to us with a large number of machine learning challenges alongside datasets to address these challenges. And then we'd collaborate with them to define well-structured AI problems on those datasets and then pose them to our community, who would then participate in these competitions and develop solutions on these datasets. And that provided a really great way to gain insights into how machine learning was evolving, as well as frictions that users hit as they're trying to apply machine learning to real problems. And based on those pain points and insights that we saw, we started to expand our platform into our community beyond competitions in 2015 with the launch of a reproducible research platform and a public data platform, as well as in 2018 the launch of a learning resource. So I'm going to dive deeper into each of these parts of Kaggle, and as I do this, I encourage you to think about how you can leverage our platform to accelerate your own data and machine learning work professionally. So first, as an introduction, what is a Kaggle competition? We run dozens of public competitions simultaneously, many with large amounts of prize money attached to them. And each of these competitions has a very well-defined AI problem. I'll just walk you through a simple example first. This is on applying regression techniques as a getting started tutorial competition to predict the house prices. And we'll start with a data set from a competition host with a target variable on it. So in this case, we're trying to predict the sales price of a home based on a small number of things like the size of the home, whether it's a home or a condominium, the size of the lot it's on, things like that. We will take the data set from the competition host and figure out a good way to split it into a train set and a test set. We will then release the train set and all but the solution on the test set to our community. who will then train models on the training set and make predictions on the test set, and then submit their predictions back to us. We will compare their predictions to the ground truth, and then calculate scores based on those predictions on a public and private leaderboard. Then the really important part of this is participants see real-time feedback on how they're doing in the competition on the public leaderboard, both their own score and performance in the competition, as well as how this compares to every other participant in it. And this creates the dynamic that really drives the progress of the competition forwards, because it's the difference between a user making 1 or 2 passes on the problem, feeling pretty good about themselves or pretty bad about themselves and giving up, and saying like, oh wow, how did this guy get, or this person get ahead of me, and then wanting to try improving their results to match or beat the performance of the people in front of them. And over time, this dynamic drives the competition to extract nearly all of the usable signal from the dataset, potentially limited by the inherent noise in the problem, as well as any limitations in the current state of the art in the machine learning. So what this graph is going to show is it's going to graph the competition progress over time and the top score on the public leaderboard over time. So what typically happens is pretty quickly we get a submission that's a decent improvement over the benchmark in the competition. And then that submission is beaten by another submission that is also a pretty large improvement. And this dynamic and leapfrogging occurs a couple times early in the competition until we hit a point where it's very, very tough to improve the results beyond that. Even with an increasing number of teams participating and people trying to tackle this problem, we don't see a large increase in performance. And this is a really promising sign that we've hit the limit of what is achievable on this data set, given the current limitations of the state of the art, as well as any inherent noise in the data set. And this is a sign, if you're managing a team of machine learning engineers as well, that you don't want to invest more in trying to improve the machine learning piece of this problem. Maybe if you're trying to improve your performance beyond that, you should be collecting a lot more training data. You should be doing some other aspect of the problem that isn't based on the current data set that we have to work with. Then another kind of really unique aspects of competitions is even though there's a competitive dynamic driving them, most participants in the competition are not trying to win. They're coming to learn and improve their skills, and this results in a highly, highly collaborative, helpful, and detail-oriented competition forums where people are sharing what techniques work well on the problem, as well as insights that they've learned, as well as if they get stuck, helping other users get unstuck. And this is just a quick example of some forum posts that you'll see the kind of really practical, detailed tips required to do well on the problem versus broad statements. And then at the end of the competition, final results are unveiled on a private leaderboard for both prize money as well as recognition. And to take a step back, probably the most famous machine learning algorithm in the US is the Zillow's estimate score for estimating house prices. And we collaborated with Zillow at a competition recently that involved predicting future house price sales and out-of-time samples. And this actually improved on the estimate by 13%. So this provides a really concrete example of how this dynamic can help improve real-world machine learning results. If we look at user profiles on Kaggle, a user's profile will highlight their best Kaggle results and really showcase here's how well they can perform on applied machine learning problems, and can be a critical part to helping many of our users find jobs and transition into the field and get hired. And alongside this, we maintain a global ranking of all top Kaggle competitors over time. The next question I wanted to tackle is, what use cases do our customers tackle with Kaggle AI competitions? And my goal is to give a broad overview now of the different use cases that we tackle. This isn't going to cover everything, but it's going to be a representative sample. The first set that's become really prominent in recent years, based on the combination of the success of deep learning, as well as widely available image data sets and cost-effective human labeling, has fostered a large growth in computer vision competitions. And these range from image classification, object boundary detection, and object recognition to environmental problems like detect facial recognition in whales, or counting how many sea lions that you see in images there. Subset of this category that I'm personally really excited about is using automated methodologies to improve medical imaging results and start to tackle the challenge that we only have a very small number of trained physicians in the world who can, relative to the size of the global population, who can read these images, and that means that we're missing results on a huge fraction of the population. One example of that was we collaborated with a company called Mobile ODT that's developing a device that can be attached to a cell phone for cervical cancer imaging, and then can flag if it's for patients in rural Africa, if they should be seeing a doctor in a follow-up visit and going to an urban city to see a doctor in a follow-up visit on that. A third broad category, moving back to the online world, is around recommender systems and personalized recommender systems, where these have been very effective at improving results ranging from consumer products to things that are directly useful for machine learning engineers as well, like recommending which R packages you should be using in your day-to-day work. Another kind of distinct and more challenging step is forecasting product demand over time on out-of-time samples, where you can no longer make the assumption that past performance or past results are going to be drawn from the same distribution of the future results. And this introduces a really complex time element into the machine learning models and the forecasts that need to be done for tackling these challenges. Another broad category that is a really important challenge to solve is improving our ability to apply automated methods for text and speech understanding, especially with a large increase in online content recently, and everything that that entails. And then finally, looking at some more industrial use cases, we've started to see an increasing number of predictive maintenance use cases for predicting which parts will require maintenance over time in advance of the part failing and the maintenance being required. So next, I want to look at what insights have we learned from seeing how users approach these competitions. And the first is probably everyone's favorite topic when they look at what works well in machine learning, which is what tools and which techniques work well. Over the past several years, that has had a really pithy summary, and that there's types of techniques that have been omnipresent in winning a lot of different types and diverse types of Kaggle competitions. The first are flavors of ensemble decision trees, like gradient-boosted machines, with XGBoost as one of the really common, successful, high-quality implementations of that. And then secondly, deep neural networks for richly structured natural input, like computer vision data, with Keras as being one example of a really popular library implementing that. And we actually recently surveyed Kaggle winners since 2016 for which primary ML framework were they using. And then you see this coming out here, where we have 3 deep learning frameworks that stood out as the primary framework the winners had used: Keras, PyTorch, and TensorFlow. And then 2 ensemble decision tree gradient boosting machine frameworks, LightGBM and XGBoost. And these are so widely used, both because of their ease of use and ease of getting started on challenges, as well as the ability to go really deep and iterate quickly and expose the complexity when you need it in improving the machine learning algorithms that you're using to tackle the specific problem. We also added a secondary question to that survey for what auxiliary ML software tools are you also using to compete in competitions. And the one that really stood out here is scikit-learn was rarely used as the primary tool by the winners. However, the feature preprocessing and the feature selection and ensembling techniques that were present in it were a highly helpful auxiliary tool for our different winners. From a process standpoint, we've also had one clear lesson that has stood out from hundreds of winners' interviews, and that is the people who do well at applying machine learning do not take a complex idea, then try that one complex idea over a 3-month to 12-month time period. Because a lot of ideas that we start off with are bad. Instead, what they do is they optimize their workflow for learning and experimenting through a lot of bad ideas to find the ones that actually work or start working well, and then really honing in on the ideas that work well. So instead of trying to implement one large and complex idea, they instead try many ideas over time, implement them quickly, take rigorous evaluation, evaluate how they work, analyze their results and what they learned, then go through this cycle again and again and again. And the teams that perform well are the teams that are effective at both going through the cycle many times, as well as paying close attention to what they were learning from going through the cycle. And in a similar vein, this iteration is not just done on the singular machine learning component. Instead, for any applied AI model, you go from an end-to-end component from a business problem to a production system that includes finding source datasets to use. How do you split the data in order to do your internal evaluation, as well as your final evaluation samples? Which evaluation metrics to use, how do you extract features and select features, how do you train your model, how do you do model selection, and then finally, how do you implement that in the production system? Our competitions don't currently tackle the first piece and the last piece of that in darker blue, but we have some of our competitions tackle the end-to-end pieces in between those. And it's critical to optimize those entire workflows, not just that machine learning piece in the middle there. And given this rapid iteration and a large number of experiments that our users are running, another key piece that successful participants do is they keep very careful track of all their experimental results for what they're learning, as well as using version control so they can scroll back at a point in time when they need to go back to an idea that had some promise and pull that back up and really understand what had worked about it and what drove that. Another piece and this has been true for almost all of the several hundred journal competitions that we've run, is that they've been won by large ensembles of models versus a single model. And these large ensembles almost always eke out very marginal additional gains. So it's like the single best model in there might be 99.9 or 99.5% of the best performance. Then that additional 0.5% performance improvement comes from taking a large number of different complex models and combining them all together, which is great for squeezing out the last bit of predictive accuracy. But putting my software engineering hat on, it's about the last thing I'd want to put into production. So instead, we'll focus on that single best performing model within that ensemble. That is the one that might make more sense to put in production. Another lesson that we've learned is successful participants very carefully analyze how does their model generalize on new data points and try avoiding overfitting. One of our users learned this lesson the hard way when he watched himself fall off the leaderboard in the final minute of the competition when it transitioned from the public leaderboard to the holdout set in the private leaderboard. And I don't think he's overfitted competition since then. So I want to talk a little bit more about where we are going with Kaggle AI competitions. Almost every competition that we've run so far has been of the form, we have a training data set and a test data set. Users download the training data set, make predictions on the train a model in the training data set, make predictions on the test data set, and then upload their predictions to Kaggle. Uploading predictions is limiting in a number of ways. So we're starting to expand the competitions that we're hosting beyond uploading predictions and to running uploading code and using the code as a submission. So the way this works for a small number of competitions now is users will write the code to train the model and make predictions of it through a hosted Kaggle code execution service that we run, and then submit that code to Kaggle. A couple examples of this where it's been really helpful to enable us to run these competitions in a high quality way is two of them have touched on backtesting and forecasting time series in a financial modeling problem, where for any time series challenge, you don't want to have a single trained data set and test data set, and instead you want to stream the data into the model over time and make predictions going forward at each time increment. It's also helped us run more effective competitions around challenges where a human could go through and label the answers to the results, because we can now run competitions on hidden test datasets where a human can actually go through and hand label the results to the test set, like for text or image competitions. And then finally, it's let us experiment with competitions around adversarial learning, where we have a really fun cat and mouse dynamic where, let's say that I have a picture of a cat, and I want to trick my classifier into thinking this is a picture of a dog, not a cat, by making small and perceptible modifications to that picture. And then we ran a series of competitions around predicting models that modify images to trick classifiers, as well as models that should classify those images and be robust against those adversarial attacks. And in the future, this will unlock a bunch of exciting new flavors of AI competitions, ranging from backtest and time series and live data feeds to reinforcement learning challenges, where instead of a machine learning model making predictions, you have an agent that's taking actions and interacting with an environment, and is scored based on how it interacts with that environment over time, as well as generative modeling competitions, where you're creating new images or new text samples and evaluating whether or not those images or text samples mirror the real distributions. Adversarial learning competitions as another one that I mentioned. Another area that's become increasingly important as machine learning's moved out of research and into many applications throughout the world is machine learning under computational constraints. Because if you're implementing machine learning at scale, it is very costly to do the machine learning predictions, and takes both in terms of dollars and energy usage, as well as there's a lot of scenarios where you want very low latency and low energy predictions. For example, I could have the best speech recognition model in the world, but if I'm in a low connectivity scenario with my cell phone, that model is useless to me if it can't run quickly on my phone. And then finally, it'll let us run competitions on sensitive data sets where we cannot release the data set publicly, but instead we can bring the code and the models to the data sets privately. Now, as I mentioned before, we spent most of the past decade or so focused on building and expanding AI competitions in the community around that, but more recently we've been building beyond AI competitions as well. I wanted to talk a little bit about our motivations for that. So the global community that we built around competitions has provided a lot of insight for current frictions on applying AI through our experience working with hundreds of hosts and organizations around the world and seeing their frictions that they structured in creating machine learning problems and pulling the data sets for those. From our experience in working with our users and seeing how they started tackling problems and all the frictions they hit doing things like sharing code with each other, as well as from our own internal work. And I'll summarize some of the ones that have served as inspiration for me and for us as we start to expand beyond competitions. The first is that we've hit many barriers to accessing data, which still lives in silos within different organizations and many different forms. And then once we do have access to that data, understanding the context behind the data makes you feel like a detective, and getting that data into a high-quality state, it can be really tough. For a couple of examples that we've hit trying to clean data, one of them is I was working with a data set of flight arrival and departure times where we're training models to predict how long a flight will take. And then on the first pass of it, I was surprised to see that I had a bunch of flights that had negative duration. Then I was thinking, oh, OK, I must have had messed up the time zone processing in my code or something like that. Did I look at that? No. Time zones were right, including for flights taking off and landing in the time zone. For whatever reason, there's just a couple percentage of these flights that were put in incorrectly as actually landing before they took off, which made no sense. As another, and then if I'm trying to make a model to predict flight durations, then I naively throw a bunch of flights with negative duration in there. That'll throw my entire results way off. As another example, I was working with a data set of bulldozer prices, and one of the fields as an input into that was the year the bulldozer was manufactured. I was flipping through that and see things like 1983, 1995, 1972, and thinking, OK, this makes sense. Then I start seeing a bunch of fields that say 1,000, 1,000, 1,000, and bulldozers didn't exist before the steam engine. and didn't exist in the year 1000. And it turns out that somewhere in the complex set of processes to create that data set from a lot of different sources, one person decided, you know what, 1000 is a great number to use as a missing value. So 1000 just meant that they didn't know when it was manufactured. And as a third example, we were working with a data set of essays that we had, student essays, that we had transcribers go and digitize those with the instructions that if you can't read the essay, please throw it out and don't send us the data back for that and mark it as you can't read it. Instead, we're starting to train some baseline models on this and saw that there was one essay in there that, and these were supposed to be about 1,000-word essays, that just said, this essay got good marks, but as far as I can tell, it's gibberish, that scored very highly. And if I'd actually thrown that into a machine learning model with a very small number of data sets, that would have really thrown my model off because it was a case where the transcriber didn't follow the instructions. Then pretty much any data problem like this has a large number of examples where you really need to dig deep into the data set to understand the context behind its created and what errors may exist with it to successfully apply machine learning models that work well on it. And another flavor of that is understanding which forms of leakage may emerge in your data set. It's a really common and subtle problem for a lot of machine learning applications. Leakage is where you're trying to use information to make predictions on the new samples that you don't actually have at the time of making predictions at new samples, or is invalid to use for predictions on new samples. And one example of this is we got a data set a while ago on prostate cancer surgery, or prostate cancer prediction, and trying to predict whether the likelihood of a patient to have prostate cancer. Had a couple hundred fields in there with kind of obscurely named that we didn't know what they meant, so we trained a baseline model on it, then looked at what was driving the results. And it turns out this innocuously named feature, ProsSurge, was kind of buried in the middle of that represented this patient had had surgery for prostate cancer. So it's highly, highly predictive of whether or not the patient was likely to have prostate cancer, but was entirely useless in applying it in any new patient scenario. Then another of the kind of common pain points that we've seen is reproducing others' work can take a very long time, whether it's work that I'm going back to work that I did 4 years ago, I'm trying to take work that my colleague did and run it on my machine, or even worse, starting with a rated paper that's published online that I'm really interested in, that I don't have the code data or maybe even the computational equipment that was used to produce that, and trying to reproduce those results. So this is probably one of the largest waste of human capital and resources in our field, in that we spend a tremendous amount of time simply trying to get to the same result that someone else had, and working through package conflicts, version conflicts, different data sets, and a large set of errors there simply to reproduce work that someone else had already did. That brings us to the first product that we launched to try starting to address some of these pain points. I see a lot of the frictions I mentioned as like aspirational long-term goals, and if we could even make a small dent into those, then we can create some real good in the world. So first we launched a feature called Kaggle kernels, where you can now click new kernel on any competition or data set on Kaggle. And this will enable you to spin up an interactive script or notebook session in Python or R on that data set. And in a Docker container. And you, within seconds, will have a source code editor, an interactive console, and the raw data at your fingertips, so you don't have to do things like install packages, because we have most of the Python and R open source package ecosystems installed in there for you. You don't have to worry about downloading the data or going and getting the data or anything like that. It's also easy to monitor things like your compute usage and add GPUs or additional compute if you need to in this. And after you finish coding or get to a stopping point, you can click commit and then create a shareable and reproducible version of your work in a clean environment. The reason we rerun things in clean environments is I've seen a lot of Jupyter notebooks where It might have 15 cells in it, but those 15 cells have been ran about 1,000 times, and that what was in the cell included a lot of hidden state that was necessary to reproduce the work, so it's not actually reproducible. And then from here, you can share your kernel with collaborators or make it public and share it with our community. And then we've had now about a very large number of high-quality kernels shared publicly on Kaggle, over about 200,000 now, of which about 50,000 have at least one upvote from another user as a rough indication for like another user found this valuable, and this is a higher quality result. And in practice, this means we now have a really rich array of content for basically any type of data that you might be working with and machine learning problem or visualization problem that you might be trying to tackle. You can find an example of how to do that in a public data set on Kaggle. So it's helped provide a really rich array of tutorials that you can use to get started with. And furthermore, because of this is being backed by versioned compute, version data, and version code, it's straightforward to fork others' kernels that they have shared here and reproduce the work that they created, as well as interact with their examples and extend it into your own. So I see a kernel as combining the three critical components for reproducible data science. The first is versioned code, the second is version data, and the third is a versioned computational environment through Docker containers. Then things on Kaggle are mostly reproducible in the sense that you can still do things like not set the arraydom seed, or if you're using parallelism, a lot of functions that use parallelism have a dependency on the time they take to execute and for whatever results are returned, so it's not reproducible in that sense, but it's reproducible in many of the core senses. That brings us to one of the next questions we face. Well, we've launched kernels and competitions, but I want to load new data into that kernel as well. How do I do that? And that led us to launch Kaggle datasets for two different reasons. The first was to provide a versioned and reproducible data store to load data into kernels. It was straightforward to drag files up and drop them in where they're in a versioned way for future use. And then secondly, to provide a interface where it was easy to share data in a high-quality way to the rest of the world. And so over the past couple of years, this has grown really dramatically, and about 15,000 datasets have now been publicly shared on Kaggle. And my longer-term goal is to have all the public data in the world accessible through a common interface like this. So I no longer, if I'm trying to work with weather data, for example, have to go to an FTP server from NOAA to try getting that obscure weather data I'm trying to pull in, or trying to dig through a complex data dictionary from the census to understand what does this field in the census as one of the most commonly used data sets mean. Then all of these datasets are downloadable and browsable in a web UI, and we're really targeting making these datasets easy to consume, both for humans and machines. So the machine piece is connecting it to Kaggle kernels and for ease of use for consumption in Python and R, and the human piece is providing clear summaries of what's in the data for things like histograms, the number of unique values in a field, the number of missing values in the field, as well as collaborative human-written descriptions of like, what's this column mean? What does this file mean? What's in this file? And components along those lines. And these datasets link all the code that users have publicly shared on top of them as well. So if you go and publish data on Kaggle, you get the advantage of seeing how that is used and how other users have built on your dataset and created code on your dataset. And then if you're trying to get started on the dataset, then you don't just start with an Excel spreadsheet or a CSV file or the file itself. Instead, you start with, here's 1,000 different code examples that other users have written on it for how to read that data in, how to visualize it, how to pre-process it, how to apply machine learning algorithms to it, and things along those lines. And then after we started to build up all these resources and create all this content on Kaggle, we started to get the question more and more, I want to get started with machine learning, and I do not know where to go. What should I do? And that led us to start building a series of micro courses with tutorials and interactive exercises, with a goal of providing a really fast and straightforward way for users to get started in the nearest way possible to get them onto their own projects and their own work. So these range from beginner content like Python, interest in machine learning and data visualization, and Pandas is a really nice data manipulation library in Python, to more advanced content like machine learning explainability course, where we want to really help users understand that seeing machine learning models as black boxes is a really common misconception, and there's a large number of tools and methodologies available to you to introspect a machine learning model and understand what is driving its performance and why is it making the predictions that it is. So that was a broad overview of the different pieces of Kaggle's platform. I hope that was helpful for you to understand the different components of what we're working on and why we're working on them, as well as when you're trying to solve your next machine learning or data problem. Hopefully this will be a helpful resource for you to go to and find an example as a source of inspiration, or see how another user has tried to tackle a similar problem as you and use that as a starting point versus needing to start your work from a blinking cursor.